think we can start.
Okay, let's start then. Let me share my screen. So are there any questions before I begin? Okay, then let's start with the lecture. So today's lecture is about testing. And I think this is a very nice use case for Haskell, or like a nice argument why Haskell is really special and great, because the way we can do tests in Haskell is much more powerful than in other languages. Although these days a lot of languages have tried to copy this idea that I present today, but it originates from Haskell, and only in Haskell can it be like exploited to its full power due to the special properties that Haskell have that we talked about, like referential transparency and things like that, and explicit effects. Right. So talking about testing versus types, then introduce quick check and so-called property-based testing. That's the testing paradigm I'm talking about. That's so much more powerful than the unit tests you're used to from other programming languages. Then we'll do some examples and talk about a bit more about how to write these tests. And in the end, if you have time, we also talk about coverage. So there's a tool that basically can display in a nice way how your tests cover your code. Okay, so let's first talk about testing in general. So, I mean, why do you test? In order to gain confidence in your programs. I mean, ideally, your program should be so obvious that they're basically self-evidently true or correct. But of course, if it comes to more complex scenarios, then that might be impossible. And you really need some tool, some testing to convince yourself that your program actually does what it's supposed to do. I mean, there are some people that say about Haskell, when it compiles, then it works, which I personally find is almost true. So I find that in Haskell, once something compiles, it indeed often immediately works. But of course, in principle, there can still be bugs that the compiler can't catch. And so with tests, you can check that the common use cases work as expected, but in particular also that corner cases, edge cases work as expected. But of course, it's important to keep in mind that testing cannot prove the absence of bugs. No matter how much you test, you can never be 100% sure that there are no bugs, but you can basically improve your confidence as much as you want, depending on how much effort you're willing to put into the tests. And the point is that in Haskell, with this property-based testing that we're going to talk about, you can get in much more confidence than in other languages by just writing unit tests. There are languages where you can actually prove the absence of bugs, languages that are actually based on Haskell, but those are not really languages that are used in production. So I'm talking about languages like Agda or Idris, where you can actually do proofs of correctness in the programming language itself. But that uses, I mean, those languages use even more powerful type systems than Haskell does, where you can actually, in the types, encode properties. So for example, in these languages, you can write a function that sorts a list where the type of the function already guarantees that what you get out is the sorted version of what you put in. And then once you get that to compile, you don't need tests, because then the compiler indeed proves that your program is correct. But as I said, that's not really widely used and not very practical. It's normally a lot of effort. So the more pragmatic way is what Haskell does. I mean, it's not a mathematical proof of correctness, but it allows you to be much more confident than in many other languages. Okay, and there's one exception, of course, where you can prove the absence of bugs if you only have finitely many input cases. I mean, if you have a function, for example, like the logical disjunction that we talked about, logical OR, there are only 4 input cases. I mean, true, 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 false, false, true, and false, false. So obviously, if you check those 4 cases and verify that they give the correct result, then you have indeed proven that your function is correct. But of course, most functions in the real world are not like that, and you have infinitely many, or at least a lot of potential input cases that you can't all verify one by one. Right. I mean, first, of course, I mean, what does it even mean for a program to be correct? I mean, I think we all have an intuitive idea what it's supposed to mean, but to formalize that is actually not so easy. I mean, you need some sort of specification. I mean, you need to document or in whatever form way to say what the program is supposed to do, and then you can compare what the program actually does against this specification. The question is, how do you make that link? I mean, often specifications, I mean, a lot of times they're just in your head. But I mean, maybe if you are more meticulous, then you write the specification down before you start the program. But often those specifications are just prose written in English or Swahili or whatever. And then, of course, it's impossible to make a formal link between the program and this document. There are also ways to do this in a formal language, so basically a machine checkable specification. And in some sense, what we're talking about today is property-based testing goes into that direction. So you can see the tests as a specification of your program. I should also mention that the Cardano node and Cardano in general, I mean, I mentioned in the introduction that one thing we are very proud of is the Cardano approach, science first, research first. So all we do is based on solid peer-reviewed research. But of course, there is still this problem. I mean, even if you have a perfect, beautiful cryptographic paper, like the ones that describe the Ouroboros consensus algorithm, how do you translate that into actual software? I mean, you get this paper written by our scientists, and you have to produce actual software that runs on people's machine. So how do you, I mean, and even if the paper is perfect and there's no error in the proofs anywhere, how do you make sure that you translate what is described in the paper into something that actually does what the paper says it should do? So we have put a lot of effort into trying to make that as airtight as possible, this transition from the mathematics in the beginning to the actual engineering. I mean, there's still, I mean, you can't do everything automatically because these research papers are, of course, also written in English. So somehow, I mean, a human must make this transition from this English document into Haskell code. But we do, as I said, put a lot of effort into that. And these property-based tests that we are talking about today play a big part in that. So basically what we do is, I mean, we take the original English paper and then write a very high level formal specification of that, which is basically written in Haskell. But that is code that's not really performant. It wouldn't be efficient. But it's obvious, in air quotes, correct. So, I mean, nothing, of course, is obvious, but the idea is it should be easy for somebody that understands the science behind it and some Haskell to look at the Haskell code and at the paper and then see that the code does exactly what the paper says it should do. And then we use this spec, this Haskell spec, basically to test it, to test our real implementation with it. So you can think we run them in parallel and check that they always produce the same result. And that's one way we try to make sure that this translation between research paper and software is actually correct. We also try to actually formally mathematically prove correctness in some cases, but that is extremely resource hungry. So you need a long time to prove formally that software is correct. I mean, normally that's only done in like space travel or for like medical instruments or for aircraft software and things like that. So we use some of these techniques, but it's not used for everything because that would just be too much effort. One last point here is that, of course, the specification can also be wrong. So, I mean, you have an idea of how your program is supposed to work. You write a formal specification, and there can be errors in that formal specification as well. So then when your tests find that the test fails, that doesn't necessarily mean that you have found a bug in your program. It could also mean that there's a bug in your test. Was there a question? I just heard the ping.
Yes, someone raised their hand.
Okay.
But they retired the hands and
Okay.
raised the hands. So
Okay. Right. And so now there's testing versus types. So do types free us from the need to test? I mean, I think for somebody coming from Python or so, that this question doesn't even make sense. But Haskell has a very strong type system. And that's also, I mean, what I said earlier, that some people say once it compiles, it works in Haskell. I mean, the reason for that statement is that there are a lot of things that you can express. And I mean, the idea is, I don't know what the exact quote is, but the idea is to make like invalid data unrepresentable. So often
invalid states.
invalid states unrepresentable.
Yeah.
Right. So I mean, if you have a very like untyped language or not very strong type system, then often, I mean, if something like a state of your program is of a type, then there can be invalid states. I mean, states that should never happen, but they are still valid values of that type that you use. But in Haskell, it's often possible to prevent that, so that in the types you can express that only, I mean, the only values of that type are actually valid states. The stronger your type system is, the easier that is, and the further you can push that. I'm trying to think of an easy example. I mean, I don't know. I mean, for example, with null. I mean, null in other languages. I mean, a lot of languages have this null value. Everything can also be null, and then you always have to check for that. And I mean, in Haskell, for example, we don't have null, so that already I think reduces common bugs in Haskell. So I mean, there are many fewer bugs. Trying to think of a good example for being able to, yeah, do you
I
have?
mean, if you have a function that can only take odd integers, every time you use it, you use it, you have to like check if the number is odd before using it. But if you create a type that can only contain odd numbers, then there is no way you can use the function with different not odd numbers, with even numbers.
Right, that's true. Yes. However, it's I mean, of course, you can do that in Haskell, but maybe it's not so easy to. I mean, I could write down a type that represents odd numbers, but it's maybe not so direct. Can anybody think of a more obvious example?
The non-empty list.
Right, that's a good idea. Right, that's a good idea. I mean, we have this example code again. Let me just, as always. Right. So let's say you have, I mean, a scenario where you work with lists, but they are supposed to be non-empty. So you have at least one element. And I mean, we talked about this head function last time. So I mean, we have this head function in the prelude that a lot of people hate for good reasons. I explained last time that this can't possibly be a total function because for the empty list, there's no way to conjure an A out of thin air. So it must crash on the empty list. And I last time I said there, I mean, a better alternative probably would be to have safe head, which takes A to maybe A. But another way would be to just in the types forbid that the list can be empty. And there's actually a type in the standard libraries, it's called non-empty. But I can just, I mean, that's defined something like this. So it's, I think it's called non-empty A. And it's defined something like this. Let me see.
You don't
Oh,
need
yeah.
the
Sorry. I don't need the non-empty. Sorry. Yes, of course. Right. So here the idea is we just define a type of non-empty list. And how do we do that? Where we say a non-empty list always has a head. So there is always an A. And then there is a tail, and that tail is an ordinary list. I mean, that can be empty or not, but we always have this. And I mean, we can, for example, write an easy conversion to list on non-empty A to A, which just takes, I mean, I should switch off Copilot again, but like this. So each non-empty list can be obviously converted into a list, but the other way won't work because, I mean, if we have the empty list, we can't produce this A here. And then I can write a head, a perfectly safe head from non-empty A to A, which just takes such a list. I don't care about the tail, and I just produce the X, and I'm guaranteed the X is there because, I mean, this is the only constructor. I always have this A. Yeah. So I can. So that would be a simple example of what we just tried to explain. So, I mean, because you can simply define a type like this. So if you are in a situation, so you have some list, but you know this list will never be empty. Then in other languages, basically you can just, I mean, you make a comment. I mean, if you have this type, then you make a comment and say, this should never be empty, or this can never be empty. I mean, in words, in English. But in Haskell, you can instead just define a new type or use an existing one. As I said, this non-empty type is actually in the standard libraries, in the base libraries even, I think. I'm not sure. Maybe it's in containers. I think it's in the base library. And
it's in base. And we also have natural numbers in base, I think.
But they I mean, they only check at runtime. I mean, they don't, the compiler doesn't enforce that it's never negative.
Right.
But yes, we do. Right. So the point is then you could, instead of using lists, you would use this type. And then you don't have to write this comment, and you don't have to, like by hand, always check that it's indeed not empty, and always think about that. Then it's guaranteed. And the compiler will make sure whenever you produce a thing like this, you indeed have an element, because in order to construct such a non-empty list, you really have to provide this element. So that would be a simple example. And I mean, there are lots of examples where you can make data more, I mean, where you can, as Robertino said, so invalid states are not representable. But you can't always do that. Or at least, I mean, these days you probably maybe can almost always do it. But I mean, if there are cases where it's not worth the effort. I mean, there's a lot of, like, especially in recent years, machinery that you can use in Haskell to express very complex invariants in the types. But at some point, the work you have to put into that is just not worth it. But anyway, at least, I mean, with simple things like this one, for example, you can already push it very far. Maybe I think there's no lecture or slide on phantom types. I'm not sure whether this is a good idea to talk about that now. Maybe. I mean, another thing that in other, I mean, let's say, I mean, a lot of things are strings. So let's say you are writing some sort of application and you have, you think, well,
A
yeah.
guest or a login user, a user that
Right,
can
right,
be
right, right,
directly.
right. Right, exactly. So for example, let's say you have some web application and you have a user type, and the user can either be logged in or I mean, can be verified, I mean, logged in, authenticated or not. But both in principle are just strings. I mean, it's just a username. So let's say, I mean, normally you would have, I mean, you would have something like type, whatever, unauthorized or unauthenticated user, authenticated user is just a string, and then maybe you have a function authenticate or is authenticated from unauthenticated user to bool, let's say. I mean, this is like situation I think would be relatively common. So somebody like comes to your website, so with a username, and then he wants to see some admin pages. So then you call this whether he's authenticated or not, and if he is, then you allow him access. But somehow in the types, I mean, it's just strings, so you don't know whether it's a, I mean, whether he has already been authenticated or not. I mean, this is now maybe not a good example for phantom types.
I
Maybe
mean,
anyway,
you can have
with the new type. Sorry.
you can have the type user
Yes.
that takes.
Yeah. I mean, there's like several ways now. I mean, how I could actually do this in Haskell. So one way, for example, would be, I mean, I can think of at least three ways. So one would be to define, I mean, to make this situation better. So the problem is, I mean, you call this Boolean, I mean, this Boolean valued function, and then, but later, if you have the user somewhere in your code, you don't know whether he has been authenticated or not. So one way would be to define a type user that has two constructors, unauthenticated and authenticated string. And then using this thing, I don't know why I deleted this. Right. So this is basically just from string to bool. And then we could now make this better and write something like authenticate user say, I mean, this is maybe, let me just, I mean, it's not perfect now. We could do is, I mean, we could call this function that we have from somewhere. And if it is, then we can just return authenticated user. Can leave it as is. I mean, this is not very good. I give a better solution soon. And if we have an authenticated user, then we can just keep him. I mean, that would be one way. It's not very good. A better way would probably be to have like two new types, new type authenticated string, and a new type unauthenticated. And then we could write a function say authenticate from unauthenticated to maybe authenticated. So we again call this function that we are given. If that works, then this, and otherwise nothing. And then, as we saw in this table example, where we showed how you can abstract the implementation of your data types, you could put this code into a module and not export the constructors authenticated and unauthenticated. And then if at other pieces of your code you demand authenticated, then the only way to get something of value authenticated is to actually call this authenticate function. So you don't need to remember whether you already checked, or you don't have to like double check and call this is authenticated again. Once you have this authenticated, you're good to go. And so that's just nice, I think. And then a slight variation of this is using so-called phantom types. So I could do something, I could define a type data, whatever, user status or something, authentic, no, sorry, I could do something like this, authenticated without any values, I don't care. So just empty data types, that's possible actually, to have data types without constructors, so you can never define a value of that. And then we could say new type user A user string. Now this is weird, and we have seen it before. We have not seen it before. So this type uses a type constructor that's not used on the right hand side. So this A is just there on the type level. On the value level, it doesn't play a role. And this is a so-called phantom type. This A. Right, and then we could rewrite this example and go from user unauthenticated to maybe user authenticated. The only difference is that the constructor name now changed. But now we see, I mean, if I hover here, so this is actually that's right? Yeah, I think so. Anyway, okay, why do I? Oh, it seems I do have, anyway. Okay. So now I have this authenticate function like this. And the same that I said before is true. So later in your code, in some sensitive areas, you work with users authenticated. And if you make this abstract, hide this function in a module, so basically don't export this user constructor, then the only way to get an authenticated user is to call this function. So whenever you see an authenticated user, you know this function has been called and he has been authenticated. And finally, in like modern Haskell, so I mean, this is just as a remark, we could do something like and then right. So I would need to add some weird language extensions that we haven't talked about and probably also won't in this course. But then it's the same idea, but now because of this, now I really don't have, it looks the same, but earlier with the thing I had before, I could also have a user int or user bool or something, which doesn't make sense. I mean, I only want to a user unauthenticated and authenticated. So now this enforces that I only have those two options. But anyway, this is besides the point. So let me remove this again. Right, so there are many options in Haskell to do stuff like that. Right, but was there a question?
Yeah. So just I wanted to point out that from now on, you can write a bunch of functions and a bunch of modules that take the authenticated user, and you don't have to worry that it's not authenticated. So that's the state that is not representable anymore. To have a non-authenticated user access something that you have to be authenticated.
Exactly. Maybe if we have time in the end, I can like elaborate a bit on this example with several modules. Anyway, so the point of this example or these examples with the non-empty list and these authenticated users was that, I mean, this first statement here, there are limits to what the type system can express, which is true, but those limits are much farther out in Haskell than in other languages. So indeed, you can prevent a lot of bugs just by using the type system of Haskell. But even Haskell still has limits. So there are things you can't express in the types or only with a lot of difficulty. So then just having a program compile won't be enough. Sorry, wrong key. Right, and that's what I just said. So even if it's possible to express it in types, it may be a lot of work. So there's normally a balance between how much effort, I mean, how much the compiler checks, and then there will always be, in practice, properties you can only check at runtime. But because, I mean, at least what we can say is that we don't have to write tests for stupid things. So a lot of tests you need to write in other languages, you don't need to write in Haskell. Like in other languages, I mean, in Python programs also, basically every function in the first line first checks that all the arguments have the right type. Or at least I've seen that in Python code. Because in Python it's dynamic, so you can never, I mean, if you have a function that's supposed to add two integers and takes two arguments, in Python you can never be sure, I mean, when this function is called, that it isn't called with two strings or whatever. So normally if you like write defensive Python code, then you would in the first line of this function first check that the arguments you get are actually numbers or integers or whatever. And that is not necessary in Haskell, of course. And then if you write tests, you would write a test that checks what happens if you call this function with two strings and make sure that you have covered this case in your code. So those boilerplate tests are not necessary in Haskell because the compiler just prevents that. So we can at least write interesting tests. I mean, concentrate on testing interesting properties that are not simply handled by the type system. And there are lots of testing frameworks available for Haskell. Here on this slide is just a list. And I think, okay, so there are like classic unit testing libraries, HUnit or HSpec. I think in this lecture I'm using HSpec maybe as an example. And then there's QuickCheck, and QuickCheck is basically the focus of this lecture, which introduces this property-based testing. And that's also quite interesting. So, I mean, that was invented by David Hughes and always forget the other one, but here, John Hughes, sorry, Kuhn Klaassen and John Hughes. And I mean, John Hughes, I think, was also one of the original people on this committee that designed Haskell. And it was dramatically successful. So it was very popular and was unheard of until this day, that something like that is even possible to do this. And it, as I said, it has been adopted by many other programming languages. But as I also said, they can only fake it. They can't make it as secure as Haskell does. And John Hughes later, basically, I mean, he's still doing Haskell, but he now these days mostly does Erlang, because maybe you have heard of Ericsson, this big Scandinavian or Nordic telecom provider. And they have like networks that process billions or at least millions of like phone calls every second, and with these and so that's like an enormously complex system. And he was basically hired to try to apply his quick check idea to the Erlang language, and very successfully. So he has found, I mean, tested their systems and found bugs that were extremely difficult to find with conventional methods. And I mean, it's very complex because everything is highly concurrent. So if there are race conditions or weird situations that only appear up under very special circumstances, and he was able, using these ideas that we are talking about today, to actually find bugs and prevent them. And I think he has also worked for like automotive. So he also tested like car electronics and also found some very subtle and interesting bugs there. And actually, if you're interested, maybe we can share a link. If you know, there's this YouTube series, Computer File. Maybe some of you have heard about it or watched it. And he, in one or two episodes, was a special guest and talked about this, and also gives a very nice example of this in action, where he talks about a bug that he found in SMSs, phone SMSs. So I think there is some bug in the specification of SMSs, and he actually finds that with quick check. I think it was SMSs. Yeah. Right. So this is what we're talking about today. And then there are like, I mean, there are some problems with quick check, and then other libraries like Hedgehog or Smallcheck that try to overcome those problems, but then they have other problems. But I mean, even with these problems, it's still vastly superior to traditional unit tests. And then there are also like test frameworks that allow you to organize your tests. So for example, using HSpec, you can like create test suites that also include quick check tests, and then with Cabal test, you can just run your tests. And I already mentioned doc test. That is completely different. So that has nothing to do with quick check. So that allows you to write comments in your code that are then actually, when you generate documentation, are also displayed in your documentation. And then you can actually check those properties or these examples, which means that I mean, it's a very lightweight way, an easy way to write tests, but also guarantees that your documentation doesn't get out of date. So it's useful to have like examples, because normally if you do this, if you write documentation with examples, then sooner or later the examples will be wrong, and nobody notices because everybody is too lazy or doesn't have time to, each time there's an update, to check all the examples again. And this doc test allows you to do that automatically as part of your build continuous integration, for example. So then you immediately notice when example is no longer valid, which is very useful. So especially, I mean, it's not quick check, it's just unit test, but I mean, it can be very useful for simple things. Right. So we focus on quick check in this lecture. And the idea is to generate random test cases. So instead of, I mean, unit tests, for those of you who have some experience with software development, you basically give one test case, and then you check that in this specific case, your program does what it's supposed to do, whatever that means. And the idea of quick check is that instead of giving one test case, you generate hundreds or thousands or tens of thousands of random test cases. And you just give a property. So we will see what that means. That should hold for your program. And then these hundreds or thousands or tens of thousands of test cases are generated. And then it's checked that for each of those many test cases, the property you expect to hold actually does hold. So instead of just writing one unit test and checking the property in one specific case, you can check it for thousands of cases in very little time and with very little effort. And right, and the program, I mean, QuickCheck, I mean, there are languages or testing frameworks where the tests are actually written in a different language, but this is not the case here. So QuickCheck is just a Haskell library, and the QuickCheck test is just Haskell. So the compiler in particular also checks your tests. And this I already mentioned. So it was developed almost 25 years ago now by Koen Klaassen and John Yu. And I already mentioned that it was adopted by many other languages, but they can't do it as well as Haskell does. Right, and I also talked about Erlang, and so your John Yu's company is called Cubic. And maybe I should also, like as advertising for Cardano, mention that John Yu was also consulting for IOHK or for IOG. So he, for example, applied QuickCheck to consult us on how to use QuickCheck to test the Cardano node. Because that is, I mean, maybe it's too early to talk about this now, but I mean, QuickCheck really shines when everything is deterministic, like mathematical properties. I mean, if you sort a list, there's no doubt about what the outcome should be. I mean, you get the sorted list out. But blockchain has this annoying property that things are probabilistic. So, I mean, we talked about that in the very first lecture, that, for example, these confirmations, I mean, it's not clear how long you have to wait. I mean, the longer you wait, the more secure a transaction is, but it's never 100%. It gets astronomically close to 100%, but it never reaches 100%. Another thing is actually, I mean, Cardano, I think I also mentioned that in the beginning, uses proof of stake. So the idea is your chances of producing the next block on the Cardano blockchain should be proportional to your stake. So if Robertino has twice as many ADA as I have, and we are both block producers, run stake pools, and he has twice as much delegation to his stake pool than I have to mine, then statistically he should produce twice as many blocks as I do. But that's only statistically. So it's I mean, it's not deterministic. I mean, if in one epoch in 5 days he produces 100 blocks, it's not guaranteed that I produce exactly 50. I mean, I could produce 49 or maybe even 60 or 30. And John Hughes basically consulted us on how to test things like that. And he actually has a way to test that this statistic property holds. And he even found a bug. So in the very first implementation of Cardano, the so-called Byron era, there were tests for this property, but they were very naive. So the team of developers we had back then, they wrote tests where they basically just tested one stakeholder that had very little ADA and another one that had a lot of ADA. And then they just checked that the one with a lot of ADA makes more blocks than the other one in a certain time frame. And they thought it was enough, or hoped that was enough. And then John Hughes came in with his QuickCheck and his new way of testing actually statistical properties. And he detected that there was a bug. And there was indeed a bug. I mean, it wasn't very dramatic, but it wasn't completely correct. So it was, I mean, in the very first version of Cardano, it was not true that the chance of building a block was proportional to your stake. There was a slight error, a very slight error. And he found that with QuickCheck. So yeah, it's and he also trained our Haskell developers at IOHK specifically on like advanced QuickCheck and I mean, like certain tips and techniques and so on. Right. So let's look at something practical. Let's say, I mean, we know that in data.list, we have the sort function that sorts a list. But let's say we didn't have that, or we want to implement our own, and we didn't pay attention in algorithms and data structures 101. So we pick a very silly sorting algorithm, namely insertion sort. So the idea of insertion sort is you start at the first element of the list and then you insert it at the correct spot in the list. Or no, actually you start at the end, I think, and then I think you assume that the tail is already sorted and now you have the head, and then the idea of insertion sort is that you insert the X at the right point in the tail. And you do that recursively. And then in the end, I mean, that's fine, it works, but it has quadratic complexity. And most of us probably know that you can sort in n log n complexity in the general case. So things like quick sort or merge sort or heap sort are much better than insertion sort. But nevertheless, so let's assume you want to implement this. And if you look at this, then probably you will spot bugs here. So it's not correct. So the idea is we have this sort function. Sorting the empty list is the empty list. Sorting a non-empty list is we insert X in the tail. And then we have this insert function giving something we want to insert into list. So inserting into the empty list, that's the only thing we can, I mean, puts it there. And if we have a non-empty list, we compare this element to the first one. And if it's less than or equal, we put the new element at the head of the list, and otherwise we recursively insert it into the tail. That's the idea. As I said, there are problems with this, but that's the point. We are talking about testing now. Okay. Let's see. I think I have this wrong. No, that's already sort of rightish. So let me just comment everything again. Let me quickly rewrite this. Was it? Let me just check. Okay, why is? Okay. Right. Sorry. X. Okay. So now, as we said before, in order to test this, we must, of course, first agree on what we mean by sorting. And ideally, the specification is as precise as necessary, but not more precise than necessary. So you don't want to you want the specification to be as short as possible, but not too short. So ideally, at least in the case of sort, the specification should completely determine what's supposed to happen. And ideally, especially for sorting, I mean, as I already mentioned, there are many sorting algorithms. There's this insertion sort, and there's bubble sort, there's quick sort, merge sort, heap sort. There are also these weird ones. I forgot the name. I mean, these outlandish ones that take forever. That's just fun. So, for example, is it called random or shuffle or shuffle sort or something? So the
Bubble
idea is,
sort. Well,
no, bubble sort is like relatively reasonable, at least. I mean, it's quadratic. But there is this, I think it's called shuffle sort, where you, in order to sort a list, you just shuffle it, I mean, randomly, and then you check whether it's sorted. And if it's sorted, you're done. And if not, you shuffle again. So that's like super, super bad, but it's correct. And there are other weird ones like that. Speaking of bubble sort, that is similar to insertion sort. And I had a colleague at my previous company, like by now, like more than 10 years ago, who didn't believe in using library functions. So whenever he had to sort a list, he in place implemented a bubble sort to do it every single time. Because he said it's so easy. It's easier for him to quickly implement bubble sort than to look up what it's called in the libraries and use that library function. So yeah, that's where I got my first gray hairs. Anyway, and the point here is ideally the specification should specify sorting, but not force us to use a specific sorting algorithm. So we would still have the, I mean, there could be many ways to correctly implement the specification, but they could all have the same result, namely, I mean, sort the given list. Right. So now the idea is that we think of the specification, or rather we approach the specification. So how would we specify sorting? So we are thinking of properties that a good sorting function or correct sorting function should have. And one such property is that if we sort a list, it should afterwards, the sorted list should be as long as the original list, right? I mean, sorting just rearranges the element. It just rearranges the existing ones. So the sorted list should have the same length as the original list. And we can actually write this as a Haskell program, as a Haskell function. Sort preserve length. So given a list gives us a Boolean. And it just checks that the length of the sorted list is German sneaking in, equals the length of the original list. So this is just a Haskell function. I give it a list, and it calls sort on it, and checks whether the new list equals the original list. I'm just trying to think whether I can try this on something. Let me try it on 5.2, and it's true. So, I mean, if I now was a Python programmer, I would write this unit test, sort preserves length 5.2, I get true, and I'm happy, and sort works. I mean, I'm kidding, but right. And now, so this is so far so good, and I mean, we could do that in other languages as well, of course. But now comes quick check. And let me just demonstrate. So I just call quick check. That is on Hackage. It's in a package which, not surprisingly, is called quick check. And it has in particular this quick check function. And I mean, we will talk about what this means, testable, and later, but but the point is this sort preserves length is actually something I can put here for prop. Sort preserves length. So let me just call this. And it does its thing, and then it gives this output. It failed. Falsified after 5 tests and 3 shrinks. So what that means with the shrinks, we will talk about later. And it gives me a counterexample. So what this means is, I mean, we will talk about how QuickCheck actually does that later. But now just point is I have this property that I think is reasonable for sort. So if sort was correct, this property should be true for every list, right? And now what QuickCheck does, it basically generates random lists and checks this property. And if it's true, that's fine. But if it's false, it reports this counterexample. And okay, and first let's convince ourselves that that's indeed a counterexample. So if I call sort preserves length on this list, I actually get false. And if I sort that list, I actually really get something wrong. I mean, obviously this list is already sorted, so I should get the same list out again, but I get the list with 1, 0. So there's obviously bug, and QuickCheck found it and gave me a counterexample. So a list where the sort function is not correct. I'm not sure how, I mean, I could mention this shrinking thing here. So what QuickCheck does is it generates random lists and checks this property. And if it finds a list where this is false, it doesn't just give you the list it found, it tries to simplify the list, make it as simple as possible. So not only does QuickCheck give us a counterexample, it normally gives us the easiest counterexample. So this is basically more or less, this is saying, I mean, it's no proof, but in principle, it's saying this property holds for the empty list and one element list. So the simplest counterexample is a list with 2 elements. And this is also something John Yu is very proud of, and he thinks that's extremely important. He says it's not enough to have a counterexample, it must be simple, because especially because of this randomness. So if you have a complicated program and you get like a very wild, complicated counterexample, it's very hard to understand what's going on. But if you get the easiest counterexample, the easiest possible one, that often gives you a clue what's happening. So as I said, this in principle tells us that for the empty list and for the non-empty list, this property holds. So in particular, this tells us that probably the problem is not with this line here with equation in line 21 and also not in 25. The problem is probably either 22 or here somewhere. So we get a lot of information. Not only do we know that something is wrong, we also get a lot of information about how to track down what is wrong. I mean, to find the problem. Right. And note that on the, I mean, it's random. So QuickCheck generates these random tests, but on the slide, we have exactly this counterexample as well. So that's no coincidence. Even though QuickCheck tries random lists and looks for counterexamples because of this shrinking thing, it, like, not always, but almost always will end up with specifically this counterexample. So in that sense, even though QuickCheck uses randomness, is sort of semi-deterministic, which is also very nice. Right, and the bug, I mean, one bug actually is here in this case. So we want to insert X into the non-empty list. We compare to the head of this list. And now we're in the case where X is less than or equal Y. But then we say, okay, fine, in that case, X can go to the head, which is true. But the error we make here is that we drop the Y. So, I mean, the Y must still be somewhere. So that's the bug. So we forgot the Y. I mean, you didn't, I did, or I also didn't. Whoever came up with this example did. Right, so let's reload and let's run QuickCheck again. Okay, and now it says, okay, passed 100 tests. Let me do it a couple of more times. You can also configure QuickCheck to, I mean, 100 is the default, but in practice, probably you should use, I mean, according to John Yu, you should use much higher numbers like 10,000 or so. But to quickly check something, 100 is maybe fine. And you can configure that, how many examples it's actually using. Okay, so this, I mean, so it has now tried like 400 times to find a counterexample. So this property seems to hold. I mean, as I said, it's not a mathematical proof, but we can be relatively confident. I mean, we have tested now for hundreds of cases that this property seems to hold. Okay, so that's that. So now the question is, have we tested enough? So is our specification in form of this property enough? Is it enough for a sorting function to preserve the length? Right. And now before we think about that, I mean, we can also generalize this. I mean, here we talked about preserving length, but we could generalize this. And in Haskell, we always like to abstract things. So, I mean, there's nothing special about length. I mean, we could think of other properties that are supposed to be preserved. So we could write something like preserves, which takes a property on lists. Sorry. Right. So which takes a function on lists that transforms lists into lists. Is it like this? Yeah. No, not really. Oh, sorry. It takes some function from A to B. No, it's from A to A. And a property of A's and an A and gives us a bool. So preserve function F and a property P and an A. And we just check that the property applied. I mean, if we apply the function and check the property, this doesn't have to be, this can be a B, sorry. This one doesn't need to be a property, it's just something like length equals P applied to the original value. And I forgot an error there. Okay, now obviously I need an equality constraint on B. And if I use this, then I could write this as preserves sort length. Or, as I told you, we can always switch between infix and prefix. I can also write this as sort preserve length. Right. Right. So now the question is, I mean, this won't change anything, so I can run quick check again. I just rewrote this, writing this maybe useful preserves function. So that, I mean, we have some sort of function like sort now, and our observation is that sorting should preserve this length feature of a list. Okay, and now to come back to specification. So now we have this is our specification of sorting at the moment. Sorting should preserve length. But is that enough? I mean, is the sort function the only function that preserves the length? Any opinions? Or are there other functions that preserve the length of a list? I mean, a function from list to list where the result has the same length as the original function, as the original list. Does only sort have this property? Or can you think of others?
The reverse function could be.
Right, exactly. For example, the reverse function. I mean, the reverse function would also preserve length. I mean, we can check that actually. So we can say quick check, reverse preserve length. Okay, and the error I now get is because quick check doesn't know what types to use it on. So let's tell it that we are talking about reverse on integer lists, and that also holds. And another example would be the identity function that just returns the list as is. And I mean, if I reverse a list, that's obviously different to sorting, or the identity function is obviously different to sorting. So that means my specification is too weak. It doesn't specify enough, because reverse would also pass this test. Right. Okay, so obviously, I mean, the obvious specification would be, I mean, after I sort, I should get something that's sorted, right? I mean, if I reverse, I mean, if I reverse, if I reverse, then I get a list of the same length, but the outcome is not sorted. So the obvious specification for a sort function would be something like, is the result actually sorted? So let's do this. So let's define a sorted function. So how do we check whether a list is sorted? Well, the empty list is obviously sorted. And if we have a non-empty list, well, we don't know. So we have to pattern match here as well. So let's see what is done in the slides. So a list with one element is also obviously sorted. Right. And okay, now on the slides we have first element must be less than the second element, and recursively the tail of the list must be sorted. And now I get this warning because, I mean, I could write this like that, of course. Right. Okay, and I don't use the X. So, like this. Okay, so this, I mean, I try to define what it means to be sorted. So I say something is sorted, the empty list is sorted, list with one element is sorted, and if a list has at least two elements, then I check whether the first element is less than the second element and whether recursively the tail of the list is sorted. Okay, and now I can write another quick check property. Sort ensures sorted. Sort ensures sorted. So for a given list, cool. Sort ensures sorted. XS. Well, I check with my shiny new sorted predicate whether, of course, I can just for practice also write this like this. Okay. So this now, I mean, the first one tested that sort preserves the length. The second one is supposed to test that it actually does what it says on the tin, that it sorts. So do I get a sorted list after I sort? So let's run quick check on that. Sort was sorted. Okay, and quick check says no. There's a counter example. Again, this list 0, 0. Okay, let's see if I apply this list to 0, 0. Sure enough, it says false. So let's sort 0, 0. So we should now get a not sorted list, right? But that looks okay. So what's going on here? So quick check says there's a bug. I mean, this property doesn't hold. and it gives me a counterexample 0, 0. But when I actually sort 0, 0 with my sort function, I do get the correct result, which is sorted. So what can possibly be wrong here? Any idea?
The specification is wrong, I think.
Yes, very good. I said in the beginning that if you find a broken, if you find that the property doesn't hold, doesn't necessarily mean that there's a bug in your program. There can also be a bug in your test. Okay, so do we know where it is wrong? Can anybody spot the bug in my specification?
It could be like x less than or equals
Exactly.
also.
Yes. So here, when I check sorted, I check for x less or less than y. But as we see in this example, in this example, x would be 0 and y is 0, and they're both, this is sorted. But according to this, what I wrote here, it's not, because 0 is not less than 0. It's less than or equal. Exactly. Okay, so I fixed this. I can check it. So, if I now call sorted on 0, 0, it gives me true. And if I now call sort ensure sorted on 0, 0, this is now also true. Okay, so now I fixed the test. So let's see whether now our test, our quick check finds another problem. Okay. Okay. So it does find, and now it and this is also interesting. We see that we always end up with the same counterexample, but obviously, we see the randomness at action here and the effect of the shrinking. So here it needed 9 random tests, here 6, here 5, here 4, and it needed different numbers of shrinks, but eventually it always came up with the same counterexample, which tells us that it's probably there is no counterexample for lists with 0, 1, or 2 elements. So the simplest list where this property is broken is one with 3 elements. We can try it. What happens if we do 0, 0, -1? Okay, and sort doesn't do anything. It gives us back the same list, which is obviously not sorted. So what's going on here? Let's look at the definition again. Can anybody spot the bug? We can also try to just basically run that in our head. What happens for this example list? So I come in with this list 0, 0, -1. It's not empty, so we are in the second equation. So x is 0, and axis is the list with 0 and -1. Now we insert the 0 into 0, -1. And it's not the empty list, it's this case. So x is 0, y is also 0, ys is the list containing -1. 0 is less than or equal 0, so we get 0, 0, -1, which we indeed get, but that's not sorted. So where does this go wrong? What's the problem? We insert the 0, the head, correctly into the tail. Yeah, somebody an idea?
Yes, I think we should sort also the excess in the
Exactly.
sort function.
Exactly. So the problem here is that the tail is not sorted. So even though we correctly insert the head into the tail, if the tail is not sorted, this of course doesn't work. So what you are saying is we should also sort the tail. Why do I get whatever? Okay, you could do that with a fold, fine. Exactly. So let's try again. Okay. Good. So now we can be reasonably sure that our sort function preserves the length and indeed produces sorted lists. So we can try it out with 0, 0, -1. And now we actually get the right result. So, but again, now we circle back. So, so now we check this and this. Is that enough? Is the specification, does it nail it down? Or are there still functions that would have these two properties, but nevertheless not sort? So can somebody think of a function from list of ints to list of ints that preserves the length and produces a sorted list, but does not sort? Or do you think we are done and this now guarantees that sorting is correct?
Mm, I
Yes.
think, for example, if we have a function that produces any amount of numbers, the same number repeated.
Right, exactly. Which is a good point to introduce replicate function, or maybe it's in, I think Karina last time said it's in the assignments. But anyway, we have in the prelude, we have something called replicate that gets an int and an a and produces a list of a's. So what it does is it produces a list of a's that's as long as this int suggests. So for example, I can call replicate, I don't know, 5 on the character x, and I get 5 x's. Or I can call replicate on 3 true, and I get a list with 3 trues. So I could do evil sort from list of int to list of int. And it just does what you said, or what I think you said. It just replicates the correct number of times, something like 42. So if I do evil sort 0, 0, -1, I get 42, 42, 42. And now let's do the same thing here. Let me abstract that. So ensures. So again, I have a function from A to A. And now I have a predicate on A. Ensures function predicate A. I check the predicate after I apply the function. And if I do this, then I can rewrite that as sort ensures sorted. Now I can also do quick check on evil sort ensures sorted. And that also passes. And I can also do preserve length. And that also passes. So the two tests I have for now, I mean, they wouldn't distinguish between sort and evil sort. But evil sort obviously doesn't do the right thing. You just coordinate with the slides. Okay, that's where we figured this out. This is where we figured that out. Okay, and the slides is called evil no sort. Fine. Maybe I should correct that. Doesn't make a difference, of course, just a name. Sorry. Okay, the slides already give it away. I mean, what's the problem with evil sort? I mean, it comes up with this stupid, now it's called evil no sort, comes up with this 42, which is obviously outrageous. I mean, where does the 42 come from? So the point is, I mean, when we say sort, of course, we want to sort the elements of the original list and not come up with some arbitrary new elements, right? So how can we check that? So on the slides, it says, you need to make the relation between the input and output lists precise. Both should contain the same elements, or one should be a permutation of the other. This permutations, is that in the prelude? Oh, it seems it is.
Yes.
Okay, so there is a function permutations in the prelude, which gives all permutations of a list. So if you try it on a short list like X, Y, Z, then we get all 6 permutations. Is there an assignment to implement that? It's not difficult to write that by hand, but anyway, we can also do it on a like an int list. Right. So it gives all 6 permutations. And we see in this case where we have a duplicate here, some of the permutations are also duplicates. So it doesn't look at the actual elements, it just blindly gives all permutations. So it's for a 3-element list, that's 6 permutations. We have a 4-element list, then it would be 24 permutations. And for a 5-element list, it would be 120 possible permutations. So now the idea is that of course the sorted list should be a permutation of the original list. So it should use the same elements just in a different form. So we can do permutes. So if we have a function from, let's say, int list to int list, and such an int list bool. So we have a function and the list, and we say, okay, if we apply the function to the list, then the result should be one of the permutations of the original list. Okay, and now we can try to test this. So start mutes. Okay, and we can try to call quick check on that. And now we have another problem. And for some reason that's not solved. That always puzzles me, and I always forget that when I do this lecture again. So how are we supposed to solve this now? Do you know, Robertino, what I did last time?
I don't recall how you did it last time, but
I mean, the problem now is that
maybe we can limit the length
yes,
of the
that
list.
right. The problem now is that, as we saw here, these permutation lists get very long. I mean, it's factorial, right? So we have, I mean, factorial of, if you have a 3-element list is 6 permutations. If you have a 4-element list is 24. The 5-element list is 120, and with a 6-element list it's 720. So that grows very rapidly. And quick check tests very long lists. I mean, up to 100 elements or so, which is an astronomical number of permutations. So that's why it's now stuck. I mean, it did 13 tests because, as we will see in a moment or after the break, QuickCheck starts with short lists and then gradually makes them longer. So the first 13 tests or so were okay, but now it gets stuck because probably it has a very long list and there are like bazillions of permutations. So it just, it's too slow. But what I can do is, if I try it with our evil no sort, I must write it like this. And there it immediately finds a counterexample. So just the list, I mean, the empty list is not a counterexample, but this evil no sort already on a list with one element that just contains 0, I mean, it doesn't sort. So we easily find the counterexample, but we do not, I mean, this, so now we have like several options. I mean, one option would be to not use this permutations function. I mean, it should be easy to check whether one list is a permutation of another without having to go through all the, I mean, first create the list of quadrillions of permutations. I mean, I could think of ways of doing that, but the one that Robertino suggests is to just restrict how long the list can be. And in QuickCheck, there are several ways. I mean, a quick one would be, it's not very good, but we could say, for example, length XS less than or equal, I don't know, let's say 8 maybe, or this. Let's try that. So for evil no sort, it still fails. So 8 is maybe too long. Did I reload? No, sorry. And oh no, what do I want? I want that. Sorry, that's the wrong way around. Like this, I want it. So this means it will always pass if the list is longer than 8, but if not, then it actually checks this. Sorry. Let me just try the evil no sorts again. Okay, there it still finds the. Yeah, okay. So this works. Maybe also with 10. Yeah, okay. So 10 is still, I mean, we see it's a bit slower, but let me just push it a bit.
I just checked, and
Yes.
last time you solved it by taking a limited amount, like 8 elements, and then testing.
What do you mean by
So you
limited?
take a list of any amount of values,
Mm-hmm.
and you take the first 8, and then test on that subset of the list.
Oh, right. Okay, that's maybe better. So it seems I can do it with 11. So what you're saying is I check that that
The same
that
test, but you first take 8
yes,
or 11.
yes. I check that Right. Sorry. So let me do it like this. So no matter what list I get, I just take like the first 11 elements of it, and then I check that sort of this shorter list is an element of the permutations of this shorter list. So I always truncate the list to 11. Okay, maybe I mean, this would work, but let's not go overboard here. Let's do 10. I should also mention, right. Yeah, that's also not a bad idea. So this basically checks it for, I mean, it has the same effect as what I did before, but it's somewhat nicer. So it checks that it work. I mean, that this property is correct for lists with length up to 10 elements. And I mean, I personally would be happy now that that sort is correct, because I mean, it's hard to imagine an algorithm that works for lists up to length 10 and then suddenly with length 11 doesn't work anymore. I mean, especially a simple algorithm like that, because it doesn't do any checks. I mean, there's no, like, it only distinguishes between like the empty list and one element and maybe two elements. So it's hard to think of why there should suddenly something go wrong with 11 elements. But I mean, another way, a better way probably would be to write a better function that checks whether one thing is a permutation of another. And I mean, we can obviously do that much more efficiently. I mean, we check whether the head is in the list. And I mean, let me write the perfect solution. Let's see, is permutation of okay, so if I have the empty list and it isn't a permutation of itself. So if I have the empty list and a non-empty list, then that's false. If I have a non-empty list and the empty list, it's also false. And finally, the interesting case, if I have two non-empty lists, well, what can I do? I check, I first find the, I mean, X must be somewhere here. And then if it's not, then it's not a permutation. But if it is, I recursively call it on access and on the list where I remove X from the right-hand side as well. So actually, I don't have to distinguish these two cases. I mean, I could, but it's easier like this. I'm very. Have we seen this find function before?
I think not. Maybe they look up.
We
talk about lookup, but not
sorry, but we don't need find in this case. We can just, okay, so in this case, I need to check whether X is in the right-hand side. So we can do it just like this. I don't need find. Sorry, I was wrong. So if X is in the right-hand side, then so far so good. So now we can recursively check the rest, the X's, but now we must be careful that we remove the X from the right-hand side. So this is a bit tricky because X could be there several times and we must only remove it once. So maybe I need a helper function for that. Remove first occurrence. So given an A and a list of A's, I want to remove the first occurrence X. The empty list, it's the empty list. And if it's not the empty list and the first element are the same, then I can just give the rest. And otherwise, I keep the Y and recursively remove my element from the tail. Right, and first occurrence X, Y. Okay, and if X is not an element, then it's not a permutation. Right, and now I get errors because of E constraints. So let's add that here. And now to my big surprise, okay, first of all, that's shadowing. And the X as well. So I mean, I could just, I mean, here I don't need it. I can call it, I don't know, U and V. And now to my big surprise, I again get an error about eq, which is strange because I said eq A. And I also get a very weird error because it says eq A1. Where does this A1 come from? The problem here is that in standard Haskell, if I have something like that, so a local definition that mentions a type parameter, then there is, I mean, Haskell doesn't realize or doesn't assume that this A is the same as that A. So one way would be to just add the eq constraint here as well. Sorry, I was a Y, a V. But this is a bit strange. So there's also a way in Haskell to actually tell the compiler that this is supposed to be the same A as that one. And the syntax, you must forgive me, looks a bit horrible. So we have to write for all A here. And we have to add a language extension, which is called scoped type variables. Then if I do that, then I don't need the constraint here. So then it then I tell the compiler that that A here is supposed to be the same as this. So if I have an constraint there, it also works here. Right, and if I use this is permutation off, then I don't have to restrict myself to lists of length 10. Then I can just say sort XS is permutation of XS, I hope. And now I can do sort permute, and now it immediately, very quickly works. Yeah, so I think this is a proper solution in this case, the best solution. Right, and what I still wanted to say, it's important that tests run quickly because we are all lazy and we all have a lot to do and we need to get our stuff done. And if it takes forever to run a test suite, then we won't run it. At least we won't run it frequently. So if running all our tests takes an hour, then nobody will interrupt his work for an hour and run the test suite, except maybe during a lunch break. So then maybe if you're lucky, you will in continuous integration have it run overnight or something. But that's normally too late. It's much better if you can run your tests all the time frequently, like every minute. But for that, it's important that they run very quickly. So it's important because that, I mean, the encouraged way to do this is basically that you run them all the time. Each time you implement something, you immediately run the tests. If you change something, you run the tests. And if that takes more than a few seconds, then you wouldn't do it. Right now, the only problem with this is, no, there's no problem. Okay, no, sorry. The problem is I should have done this here. So instead of using this permutation function, I should have said, used my new function here. Is permutation of access? Sorry. And then I can use this here. Because then I can also apply to evil sort or evil no sort. So evil no sort permutes. Right, and I get the same counterexample again. Okay, so and I think and one last thing. Now that we have this check, this permutes, we wouldn't need this preserves length check again, because permutations obviously do preserve the length. So the now perfect specification would be just is permutation off and this ensures sorted. So if you think about it, that's exactly what we want from sorting. It should permute the list and end up with a sorted list. Those two properties are the perfect specification for sort. This preserved length is not wrong, but it's implied by the permutation thing, because the permutation is as long as the original. I mean, like the ultimate test would be like is sort function. So if we have from int to int, or let's say sorts or something. So we would check that f ensures sorted and f permutes. Sorry, can't write like that. I must say f xs is permutation of xs. And now I need some parentheses, I think. Why? Right. Sorry. So fxs, sorry, sorted fxs, and then probably I don't need these after all. Right. Okay, so this would be the perfect specification in this case. So now I can, for example, check that my quick check sorts. Okay, and if I do this with evil no sort, or with reverse, or with identity, then I get errors. So this, I think in this case, for sorting functions of list of integers, those two properties perfectly specify what we mean by sorting. The result should be sorted, and it should be a permutation of the original list. Of course, there's still, that's fine, and that's correct. But this, for example, now this doesn't say anything about runtime. But that's also, I think, more or less impossible to do in quick check. So as I said before, there are better and worse sorting algorithms. So this won't be able to distinguish between like quick sort and this insertion sort. So if we import qualified data.list as list or as L, so I can also quick check that the build, I mean the one provided by the standard library works, and it also passes as it should. But this one, of course, is much better than our sort because this uses quick sort, I think. So it's much faster. Okay. Are there any questions at this point? Otherwise, it's more than time for a break. And then after the break, we can talk about how it actually works.
There are no questions in the chat.
Okay, then maybe until 5 past the hour. We break.
Okay.
Okay.
Okay. Thank you. Okay, should we continue?
Yep.
I'm not sure I'll be able to finish today, which is a pity. So we must see what we do about it. Maybe then the rest on Friday. I'm not sure. But let's just see how far we get. Right. So how to use QuickCheck. So first of all, we must import it. So we must import test QuickCheck, and that's from the QuickCheck package. So if we look at my Cabal file, then we see that here as a dependency, I have listed QuickCheck. So that gets QuickCheck from package, and then in the actual code, here I can use test QuickCheck. Okay. Then, so you import it, you define properties like we did, and then you can call QuickCheck. There are also ways to do that automatically, to generate a we did it by hand in the REPL now, but there are ways to actually define a test suite that then with Cabal test, all your properties that you defined are actually tested with QuickCheck. Right, and we already looked at the type of QuickCheck, and this is the type. So it takes something like of a polymorphic type prop, but this prop has to be an instance of the testable class, whatever that is, and it produces something in IO. And the IO is needed because, as we saw when we call QuickCheck, it prints information on the screen, how many test cases it ran, whether everything was okay or whether it failed, and if it failed, it prints like counter examples. So that's why we need this IO type, because it has the side effect of printing to the screen. And in the example we have looked at for the sorting, all our properties have been of this type, taking a list of int and to bool. And we had these three properties. And as I already explained, so by default, QuickCheck will generate 100 random lists, int lists, call this function, check whether the result is true. If it's true for all 100, then it reports that everything is okay. And if it's false, then it shrinks the list and reports a counterexample. But properties don't have to have exactly this shape. They can also have more arguments. So here's some examples. So for example, we could have a property append length, taking two lists, and it checks that if you append the two lists, the length of the concatenation is the same as the sum of the length. Here's another example with two arguments, taking two ints and checking whether plus is commutative. So m plus n equals n plus m. Let me skip those two, but do these also with, here's one with two arguments, here's even one with three arguments. So take drop takes an int and a list of ints, and it checks whether if you take n elements of the list and concatenate the result with dropping n elements from the list, you get the original list back. So let me implement this. Take drop, taking an int and a list. Take drop n access. So take n access plus drop n access is the original list. And the second example is a drop twice, I think. Yeah, drop twice. So I now have a function with three elements, three arguments, two ints and a list of ints. Twice m n access. So if let me just do the same thing. If I drop m after dropping n, that's the same as dropping m plus n. elements. Okay, and this also works. I mean, with quick check. So I can reload. I can do quick check on take drop, and that passes. I can do it on drop twice, and that fails. And we see the output looks a bit different now. Earlier we got one counter example, and that was because in our all earlier properties, we had one argument to the property. Now we have a function with 3 arguments, and we get 3 values here. So that means a counter example is if m is -1, n is 1, and the list is the list with one element containing 0. And we see why, because if we drop 1 of this, we get the empty list. And if we then drop -1 of the empty list, the way drop is defined, if it's negative, then it just doesn't do anything. So we still have the empty list. But on the right-hand side, because m plus n is 0, and if we drop 0 from the one element list, we get the one element list. So we see that this is actually not true. So I think it would be true if we ensure that m and n are non-negative, for example. But this is more, I mean, what I want to say here now is it also works for functions with more properties with more than one argument. And in this case, now quick check will generate random ints twice and a random list of ints, and then run these 100 tests. Right. And you can also go the other direction and have 0 arguments. So we can have length of the empty list, for example, just of type bool, no argument. And it's just the statement that the length of the empty list is 0. Whatever. Okay. So I can also quick check something like that. Length empty. And it says, okay, pass one test. And it's only one test because there is no randomness here. I mean, it's only a Boolean. So quick check will evaluate it. And if it's true, it's good. And if it's not, then not. So what is the second one called? Wrong. So if that's false, I quick check this, then it fails. But it doesn't give me a counterexample because there are no arguments. I mean, it's just wrong. And this, if you think about it, is just what in other programming language a unit test does. So it's just a statement. I mean, you check one special case, which means that quick check can also do unit tests. So unit tests in other programming languages just correspond to quick check properties with 0 arguments. So quick check is strictly more powerful than unit tests. Sorry. Okay. Right. So if we look at that again, then we now know that, I mean, we now know examples of what prop can be. I mean, what this testable is. So prop could be bool, or it could be functions from with arbitrarily many arguments to bool in the end. So this. So now the question is, are arbitrary argument types admissible? I mean, right now we had like int and list of ints. So can I use other types? And I can't use arbitrary types because quick check, as we now understand how it works, has to generate random values for those arguments. So quick check needs to know how to do that for a given type. And there is a type, so we will talk about that later. So there's a type class for that. So types for which quick check knows how to generate random values. And the idea, or one idea is, or actually how this class is implemented. So testable is a class with a method property that goes from prop to property. And property, I mean, we'll talk about that in a bit. It's, you can roughly think of it as Boolean. So bool is an instance of testable. and if a type is testable, and then we can also, then functions from A to B are also testable, provided A is an instance of the arbitrary class. So this is the quick check way of saying that it knows how to construct random values of type A. And it must also be showable, because if we have a wrong property, invalid property, then as we know, quick check prints counter examples on the screen. So in order to know how to display a value of type A must be in the showable class. So basically the base case is Boolean unit tests, and then functions from something to something that's testable, provided QuickCheck knows how to generate random A's and provided A is showable. So that's roughly properties. So bool is a property, and functions from arbitrarily many arguments to bool are properties, provided QuickCheck knows how to display these argument types and how to generate random values for it. I mean, we can ask for information on arbitrary in the REPL, and then we see that out of the box, QuickCheck already knows how to do this for a lot of types, in particular for tuples and lists, and then of course base types like int we have seen also knows how to generate random floats, integers. So for a lot of types it just works, but we will also, if we have time today, still see how you can write arbitrary instances for your own types. Okay, so that's that. And now something a bit more practical again. So analyzing test data. So that's about, I mean, until now we just see that, I mean, QuickCheck says it tested it for 100 random examples, but we don't know what those examples are. And that might be important. And we'll come to that in a second. So one way to get an idea is to, instead of QuickCheck, call verbose check. So let's do this. I mean, we had this QuickCheck length empty, for example. No, sorry, that was boring. The QuickCheck dropped twice, and we see here after 12 test cases, 9 shrinks, it come up with this counter example. If now instead do verbose check, then it's more verbose. So let's see what it does. So now it basically gives us all the things it tries. So first it started with 0, 0, the empty list, and that passed. Then it started with 0, 1, the empty list, and that passed, and so on. So we see also something interesting. It starts with very simple examples. I mean, 0 is arguably the simplest int. The empty list is arguably the simplest list. And then if we go down, it starts with, I mean, there are more and more complicated values. So larger ints, longer lists. This all passed. And then it finds something that fails with -6, 6, and 3. But now it doesn't stop and report this. Now it tries to shrink. So now it tries to make this simpler. So we see here, for example, it tried to change this first argument from a -6 to a 6, but that passed. So now it tries to shrink the first argument instead from a -6 to 0. That also passes. So it passes, but eventually it changes the second argument from 6 to 3, which is simpler. I mean, because 3 is considered simpler than 6 because it's smaller. And that fails. And now it tries to recursively shrink this. So the idea is it finds a counterexample, it wiggles the arguments to make them simpler. And if it finds one simpler argument that is still a failing test case, then it starts from there and tries to simplify even further. So now it shrank the -6 to a -3. And now it goes from there. Tries. Now it finds it can actually change the 3 to a 2, which is even simpler. Then now -3 to a -2, which is simpler. And now it shrinks the 2 to a 1. Then -2 to a -1. And now it doesn't find a way to make that even simpler. And that's why in the end it reports this as the counterexample. So with this verbose check, you can basically get an idea of the process, how it arrives at the counterexample. And if we do it again, then probably, I mean, we end up with the same counterexample, but we probably won't. Here, so recall earlier it was the first counterexample it found was 6 minus 6 and the list containing 3. Now this is a different one. That's the randomness at play. But by shrinking, it still arrives at the same end result. So, I mean, that's not always the case. It's not guaranteed that it will always eventually arrive at the same counterexample, but it's very often the case. And that's a nice property, that it tries to find the simplest counterexample. Right. And we also observe that test cases start small and then increase over time. And I mean, we haven't seen that yet, but there can also be duplicates. So sometimes the same is tested more than once. But this is a lot of information, and sometimes we want to somehow get a more concise idea of what is tested. And there are two or one. Sorry, just 1 second. Okay. Right. So one thing we can use is collect. So if we have something testable, testable prop and a showable A, then with collect we can combine that to a property which is testable, so we can call quick check on it. And the idea is to get some sort of statistics or characterization of our test case. So as an example, if we look at sort preserves length again, so let me do quick check again, sort preserves length. I mean, here we only see, okay, it passed 100 test cases, but we don't know which those were. We don't get a good idea. Of course, we can use verbose quick check, a verbose check, but then we get, I mean, okay, fine, but that's a lot of numbers. So using collect, we can do something like the following. We can say collect, so access, so testing a list, and then collect, for example, checking whether the list is empty or not. And now sort preserves length access. Okay, and now, I mean, so the first argument of collect needed to be showable. And in this case, because null is, null of a list checks whether it's empty or not. So that's this Boolean. Boolean is showable. And now we get in our output, when it passes, we get basically statistics about the values listed, the values that occurred for this first argument. So this tells us of these 100 randomly generated test cases, in 94%, this here resulted in false, and in 6%, this resulted in true. So that means of those 100 random lists, 6 were the empty lists and 94 were not. And this is fine, I suppose. But I mean, if, for example, this was a much larger number, then that would mean that the test doesn't test much. I mean, because it tries the empty list over and over again. So using this collect gives us insights into the distribution of our test cases. And of course, we don't have to use null. We can also do something like length. So now we basically get a list of all the lengths that occurred and how often they occurred. So for example, we see that in 6% of cases, it was the empty list. In 7% of cases, it was a list with 1 argument. In 1%, it was a list with 70 arguments. And there you need a bit of like subtlety. I mean, this is maybe now too much information. Or I mean, it's not very, because it's such a long list. I mean, we can also do things like mod 10 or diff 10. So instead of, we basically form buckets. So now we know in 32% of cases, the length of the random list was between 0 and 9. In 17% of cases, it was between 10 and 19, and so on. And in 2% of cases, so 2 test cases of the 100, had a list of length 90 to 99. So this often gives a good idea of how the test cases are distributed. And right, so this is this example here. Okay, and let's just think. Sorry. Right. So this property type is it's like a bool on steroids. It has more information, more power than a bool. But a property is also testable. One thing you can do before I come to this conditions and properties, just I want to show you. I mean, we had this drop twice, for example, or this, yeah, drop twice. So one thing I can do is I can change this here to property. And now this, of course, is not type correct anymore because this here is bool, but now I say property. But there is an operator in QuickCheck triple X, which is, I mean, I said you can think of property like booleans. So there are similar operations defined in the QuickCheck library for properties. In particular, you can, I mean, check whether two things are equal, and but now the result would be true or false, won't be a boolean, but will be a property. And the effect you can see now, if I now do this QuickCheck drop twice again, now I get the same counter example again. But now I mean, earlier it just didn't say anything. It just gave me the 3 lists. But now here, because this failed, it shows me the left-hand side and the right-hand side. So this now tells me with these 3 arguments, m equals 1, n equals -1, and list just contains 0. If I evaluate the left-hand side, I get the empty list. And if I evaluate the right-hand side, I get this list. And they are not equal, so that's why this failed. So that's one of the things you can do with properties, which makes it even easier to understand what's going wrong. Earlier, I did that by hand, and basically by hand calculate the left-hand side, the right-hand side, and said, okay, it's true that that's not equal. Okay, but now let's look at the following. First, let's define implies. I think we have done that before, or that was part of the exercises, I think. So implies. So if A, then B. And one definition, I think we already did that in the lectures, is not X or Y. And if we have that, we can do a property insert preserves ordered. So let's define that. So given an int and a list of ints, bool, yes. So if I have an X and an XS, that's the property that if I insert, if my XS is sorted, then if I insert X into XS, that will also be sorted. Okay, that's a reasonable property, right? If I have a sorted list and if my insert from above, I mean, the example we had, if this list is already sorted, the claim is that if I insert an arbitrary int into it, then I end up with a sorted list again. And that's how insertion sort worked. So let's try this. and it passes, which it should. Okay, so but now, can anybody think of a problem with this? Why maybe this is not very convincing? So let's use collect. So let's change this to property and use the collect we learned earlier. So I just want to see, I mean, I have these 100 random lists, and the statement is if XS is sorted, then inserting X into XS will also be sorted. Now I just collect the information whether the list I'm trying it with is actually sorted. So let's see. Okay, and now I get that in 89% of cases, this is false. So the list I randomly generated is not sorted. And only in 11% of cases, it was true. And I mean, the point of implies is, I mean, X implies Y is only interesting if X is true, because if X is false, then Y doesn't matter. So that means this property I'm testing here is only interesting if XS is actually a sorted list. Because if XS is not a sorted list, then this doesn't even need to get checked. And now these statistics that I gathered with collect, they tell me that in 89% of cases, the list I'm testing it with is not sorted. So basically of the 100 random test cases, 89 are boring because the premise is false. I mean, this doesn't say anything about what happens if I insert into an unsorted list. The statement is only if I insert into a sorted list, the result will again be sorted. But of the test cases, 89%, the XS is unsorted. So only 11% of the cases are actually, the XS is actually sorted. And if you think about it, that's also not surprising. Because, I mean, how does QuickCheck work? It generates a random int and a random list of ints. And I mean, if you just randomly generate a list of ints, then obviously it's quite unlikely that that list will be sorted, especially if it's a long list. So it's even worse than this. It's not only that only 11 of the cases are interested, those 11 cases are probably also boring cases where the list is very short. But I mean, the interesting cases are obviously if the XS is a long sorted list. So this example is supposed to show you that this is important to get an idea of the distribution of test cases, because otherwise you can get a false sense of security. You think, okay, check my properties and 100 tests, so that's good. But if you analyze it a bit, then you realize that actually it didn't test much. Only these small sorted lists. Only 11 of those, not 100. Well, there's one way. So what can we do about this? So one way, I mean, that properties can do is, I mean, this implies this for Booleans. In QuickCheck, there is an operator, I think it's like this. So that works from bool to property is if testable, if prop is testable. This is like implies, but for properties. So instead of using this implies I implemented here, I can use this operator. And if I now do this, then I run into another problem. So what this will do is, I mean, the semantics is like the same as before. So this again says, please QuickCheck, please check that if list is sorted, then inserting X into the list will also be sorted. However, QuickCheck now behaves differently. It will generate random X and XS as before, and then check this condition. But if that is false, so if the resulting statement would be boring, instead of just going on, it will throw away this test case and try again to randomly generate one. And it will try until either it has found 100 cases where this was actually true, so 100 interesting cases, or at some point it gives up. And unfortunately, now it gave up. So it passed 72 tests. So now it found 72 XXS pairs where the XS was sorted. And for those, the property held. But before it could get to 100, it had to discard 1,000 tests. So 1,000 times the XS was not sorted, so it had to be thrown away. And then QuickCheck throws up its hands in the air and gives up and says, sorry, I can't give you your 100 test cases. It's too difficult to make this condition come true. Okay, so what can we do about this? Right, okay, here it's different, so 41 only, so we were even lucky that we got that far. So the problem again is that if I just randomly generate a list of ints, then it's very unlikely that that will actually be a sorted list, especially for long lists. If I ask you to write down randomly 10 integers, then it's astronomically unlikely that those will be sorted. So one way to fix this is to not randomly generate arbitrary lists and then afterwards check whether they are sorted, but instead to somehow generate lists that are sorted to begin with. That would be much more efficient. But in order to do this, we must understand how QuickCheck actually generates random values for things. So that's the topic that we look at now. So custom generators. So this arbitrary class. And that arbitrary has one method called, actually it has two, it also does this shrinking. But let's concentrate on the arbitrary now, on this part. So that's the part that's responsible for generating random elements. And that's why this type gen A, where gen is an abstract type. It's not exposed by a QuickCheck. But you can think of it as a random generator for A's. So somehow it's like it's a type that contains information about how to generate random values of A's. And it's even better than this, not only arbitrary random values, but it also has this concept of simple. As we saw, the random lists that we saw, they start with the empty list and short lists and then over time get longer. So that's also somehow encoded in this generator. So it knows how to generate random values that get more and more complicated. And there is a domain-specific language. Oh, sorry, before we come to that, we can also try out these things. So there is sample and sample prime, which if we have such a gen, for example, one given by the arbitrary class, then we can just try it out. So in order to do that, we can, for example, do sample. Now we need something of type gen A, so we can use arbitrary. But then we must help the compiler to say at what type. So let's say for ints. And now sample will just print 10, I think, values that uses this generator. So this is a way to get an idea of what these generators do. And it will also increase the complexity. So we see like the simplest int is 0, and then we see that gradually the ints become larger. So if I do it again, it will be different ones, but we see a similar pattern that it starts with small ints close to 0 or 0, and then over time they get larger. We can try this with other, for example, list of ints, and we see it starts with short lists, the empty list, one element list, and then we get longer and longer lists. There's also this sample prime, and the only difference is that instead of just printing it to the screen, we get a result. We get the actual values, like a list of these randomly generated ones. I mean, you can play around with it. We saw bool, for example, is arbitrary, so we will get a. I mean, there's not much it can do, of course. It can just be true or false, or whatever. Float, we saw float, or double is also tuples. I mean, we can, for example, do bool, double, or we can try string. And I mean, same pattern. So it starts with short strings and then they get longer and use more wild characters. Okay, so that's once we have a generator to get an idea what this generator produces. And now, of course, the question is how can we, I mean, apart from something that's already in QuickCheck, I mean, these built-in arbitrary instances, how can we generate our own generators? And there's a library in QuickCheck that has helper functions to do this. So I don't know, by now I think in the assignments this random was introduced, right? So there's a random type in the base libraries that allows you to generate random A's, and using that there's, for example, this choose generator that generates random values uniformly distributed in an interval. So for example, we can try this out with sample. If I, for example, do it for ints, so I could, for example, for die, I could do between 1 and 6. And now it would, I mean, this choose generator would always produce numbers between 1 and 6, I think randomly, uniformly distributed. So each of those is equally likely. We have one off, which given a list of generators, randomly picks one of those generators and then uses it. So as an example, I could do one off, and I could use, I mean, until now we have only seen choose. So let's take choose 1, 2, and choose, let's say 100, 200. And now it basically should, so what this now does is it picks one of the generators in this list randomly. So this one or that one, and then samples from that one. So in 50% of the times it will produce a 1 or 2, and in the other 50% of the times it will randomly choose something between 100 and 200. And we can see this here sort of. Okay, then we have frequency. So that's like this, but we can give weights. So we can say it should use some of those more often. So for example, here I can, instead of 1 off, I can say frequency. And now, for example, I can say this one should be used twice as much as that one, giving these weights. And now we see that this 1 and 2 is more frequent now than the large numbers. Then we have elements, which is very simple. So it just, you give a list of possible elements and then it picks randomly one of those lists. So I can say sample elements, for example, foo, Haskell, Java, Python. And now it will just randomly pick one of the options I gave it in this list. And we have sized. So this is a bit more interesting. We talked about complexity. So that QuickCheck has a concept of simple values and more complex ones. And this you can do with this size function. So given a function from a size that I think it starts at 0, and then to a generator, it produces a generator. So for example, we can do sample sized So let's say we use choose 0n. Let's tell it we want ints. So now we see that it will always use choose between 0 and n, but when n increases, so when we want larger and larger sizes, so that starts to pick larger and larger numbers. So that's the most like sophisticated one. And now if we have these, we could write our own instances of arbitrary. I mean, of course, I mean, those specifically, I mean, these are already implemented, or this one. So the instance for bool could just use elements. And I mean, there are only two possibilities, false and true. So it can just say pick randomly between false and true. This one, I don't know, maybe that was in some assignment or example. So if we had a custom type that for directions of the, I mean, compass directions, northeast, southwest, we could write an arbitrary class by saying, okay, pick randomly one of the 4 directions. So that's easy. Now for int, I mean, one way would be to implement it something like this, to give an arbitrary int, just pick randomly in between -20 and 20. But of course, that's a bit limited. I mean, we also want larger ones. So the actual implementation in the library is something like this, using the size. So very similar to the example I gave, except I had the 0 here. So the real generator also generates negative numbers. So this says, okay, if you want to generate a random int with like difficulty level n, pick one between -n and n. So if n, I mean, it starts at 0, so there's only 0. The simplest int is 0. But when n gets larger, the generated random ints can potentially become larger and larger. Okay, and now we are in a position where we can write a generator that, or almost, sorry. I still find this a bit weird. I don't know why one can't just sort the list. Anyway, so the idea here is to write a function that, given an arbitrary list of ints, produces a sorted list of ints. And sorry, wrong. I was in the wrong editor. So this, I mean, you don't have to look too closely at this function. Doesn't really matter. So it's not sort, but we could use sort here. So I never understand why we don't just use sort. But anyway, so the idea is just, if it's the empty list, it's the empty list. If it's one element, it's one element. And now this is a bit weird. So if it has 2 elements at least, we start with the first element, but then we modify it a bit. We say make sorted. And now we modify the list like this. Sorry, abs. So abs is absolute value. Right, and we can try this out. I mean, for example, so it will produce a list of the same length, and the claim is it's sorted. I've never bothered to really understand this. Let's just take that but of course we can use quick check to quickly check whether that's true. So we can say sorted, make sorted like this. Okay, fine. So that seems to work. It's not important. I mean, don't lose any sleep about why this works. So the idea is just, we have a function that takes a list, an arbitrary list of ints, and makes it sorted. And no, it doesn't. I mean, make it sounds as if it sorts it. So it produces a different list, I mean, different elements, but a sorted one. So that's the idea of this function. And then we can write our generator, a new generator for lists of ints. Right, so we notice two things. So first we use fmap. So it turns out that this generator type is actually an instance of functor. So we can fmap. So the idea here is what this does is it will use the ordinary generator for list of ints. And remember, the problem with that is, I mean, it's very unlikely that that will produce a sorted list. So this will be an arbitrary list of ints, most likely not sorted. But then we fmap this helper function, make sorted over it, to get a sorted list, to turn this arbitrary list of ints into a sorted list of ints. So now that we know about the sample function, we can see what this does. And we see it produces nice long list of ints, but they are indeed sorted. Okay, and now the idea is to go back to this problematic property where QuickCheck gave up because it couldn't produce enough examples of sorted lists. And instead of using the standard generator for this argument, to use this generator. And then all the random cases will have sorted XS and none need to be thrown away. And how do we do this? There's another QuickCheck combinator called for all, which allows us to supply a custom generator for one argument. So we can rewrite this now. We just copy this and call it prime. And now the type changes a bit. And now the way it looks like is so we use this for all. And now use our fancy new gen sorted generator. And now basically this, and I forgot the quote. So this is now exactly like that, but the only difference is that instead of using the arbitrary instance to generate random list of ints, we use this specific generator, which we know generates sorted lists. And if we now try that and do quick check on this insert preserves ordered prime. I mean, let me first again demonstrate what happens if you use the old version. QuickCheck gives up because it just can't produce enough sorted lists. But now it passes. And I also see this collect 100% true. So it only constructs sorted lists. So I mean, this is now actually no longer necessary. I can just as well remove it. And actually, this is also no longer necessary because I know the XS will be sorted. Okay. And so this is one way to use gen sorted. Another way is to use a new type. And we could, for example, call it sorted int list. Int list int. And write an arbitrary instance for this. Arbitrary sorted int list. Where arbitrary is gen sorted. And now I need to add this new type constructor. I must fmap it over it. Okay, and if I do that, I could also write this example a bit nicer. I mean, instead of using this gen sorted, and now use my new type here, sorted int list. I pattern match over the constructor. So it's almost like the original Let's try this. Okay, sorry. I forgot I need to show instance, of course. So let's just derive that. Okay, and that also works. And we also see this collect now. It automatically, everything is sorted. So again, I wouldn't really need this. Oh yeah, this is now, was it's pool. Okay. Right. And this is actually a very useful technique. So, I mean, one way to think about it is by using type classes. I mean, either a type is an instance of a type class or not. So in this case, we are interested in the arbitrary type class, and list of ints is an instance. And there's like a standard way how random list of ints are generated. That's built into QuickCheck. So we can't just change that. But now we want a different way for generating lists because we want to generate sorted lists. And that's a problem that doesn't only occur with QuickCheck. I mean, you have that often in Haskell, that there is one instance. I mean, for a given type, you have an instance already, but now in a specific situation, you would like to use a different instance. And there are languages similar to Haskell, like PureScript, which allow that you have more than one instance for a type of a given class, and then can somehow pick the one you want. But Haskell doesn't allow that. So in Haskell, there's always either none or one instance for a given type. And the trick to work around that is this new type trick. So you wrap your type in a new type, and then for the new type, you can define a new instance. An example I can't give right now before we talk about monoids. So anyway, and this is actually something that QuickCheck does already. So this, what I now call sorted int list, there's something in QuickCheck that's called ordered list, and it's not just for ints, it's for arbitrary, probably, I mean, not arbitrary A's, but I mean, they must be arbitrary and they must have an odd instance. But then it does that automatically. And there are similar ones. So for example, positive. So if I do, I mean, sample int, as we know, sorry, it's arbitrary gen int. We know that it, I mean, now there's the -16, but here we see there are quite a lot of negative numbers. If I instead use this positive new type wrapper around int from the QuickCheck library, it will only produce positive ints. Or non-negative is similar, then it will also allow zeros. So we see zeros now occur, but still no negative numbers. Non-zero I can use. So now it will generate positive and negative, but never zero. Non-empty list. So if I do, as we know, if we do int, then actually the empty list will occur quite frequently, especially in the beginning. But if I instead use non-empty, what it's called, list int, then it will never generate the empty list. And of course, this ordered list as well. So instead of this one that I wrote myself, this sorted int list, I could just have used ordered list, that list int, and then they see that has a similar effect to what we did. So I wouldn't have needed to write this helper function and all of this. Instead, I could just have used the built-in QuickCheck ordered list new type wrapper. So give a third version with QuickCheck built-in stuff, ordered list int. And the only difference is that now the constructor is called ordered. And my God, I gave a lot of examples. So. Right, and works the same. Okay, showed that. Right, one last thing. We are almost out of time, but I'm also almost done. I mean, we had this sorted function that, remember, that checks whether, let me just change this quickly. I mean, we had it for ints, but let me just change it to make it, I mean, the same function would work for arbitrary a's, provided I have an odd constraint on a. Okay. And now let me check the outrageous statement that all lists are sorted. So sorted goes from list of a's to Boolean. So this says, quick check, please prove or check, generate 100 random lists and check all of them are sorted. And that actually, if we ignore this warning for a second, that actually passes. So all lists are sorted, which is weird. And the reason is exactly, I mean, if you read this warning, now this sorted function is polymorphic, so it's for arbitrary types, and QuickCheck doesn't know which one I want. And by default, it will take the unit type. And remember, the unit type, there's only one value. So the only value of unit is unit. So if I sample arbitrary lists of units, because there's only one value, I mean, the only thing that can change is the length of the list, but the element is always unit because that's the only element in that type. And of course, all these lists are sorted. So this is something one has to be careful about. So it's better to give it explicit type. So to say, for example, list of ints. Now, of course, it will immediately find a counterexample. Hey, you say all lists of ints are sorted, but there's this list and that's not sorted. Right, so that's that. And I think that's almost it. So, right, just as a summary, so it's a great tool. You can write properties. Test data is automatically generated. And you also have a domain-specific language, a library to write your own generators. And you should definitely use QuickCheck. But there are these days also alternatives that have like certain different philosophies, but the same general idea of generating random test cases, more or less, and checking them. So there are some details that are different. And yeah, keep in mind that your tests can have bugs too. And it still takes practice, of course, to write good tests. And then we saw examples that it can give you a false sense of security if you are not careful and maybe not testing the right thing, or if the distribution of your test cases is not good. But it's certainly better to use it than not to use it. I mean, you can still use it in a less than ideal way, but it's certainly better to have tests than to not have tests at all. And we saw that it's amazingly powerful and finds a lot of, I mean, it easily can find minimal counterexamples. So there would be one last chapter, but I skipped that now because we're already out of time. Maybe you can read it yourself, or maybe we can start with it on Friday quickly. So there's a tool, like it comes with Cabal basically, where you can get program coverage. So if you have a test suite or some program, then you can run this tool and then you get a nice HTML output of your source code. And then with colors, which of parts of the source code have actually been executed. Because that's also sometimes a problem with tests. You write tests and they all pass, but there are like parts of your code that never gets exercised by these tests because you never generate test cases that create situations where those parts of the code would actually be executed. So coverage is also a good way to see how good your tests are. Okay, and that's basically it for today. Are there any questions?
Not in the chat.
Okay. So yeah, we should definitely use Quick Check. But yeah, it takes some practice. And you should definitely check out this video by John Hughes. That's I think it's very cool. I forgot what it is, but it has something to do with SMS, where somehow something with this SMS specification is wrong, and he can actually demonstrate. I mean, he uses Quick Check to problem. That's very cool. Okay, then if there are no questions, then thank you very much. And I'll see you again on Friday then.
Thank you, Ross. Thank you, everyone.
Thank you. Thanks, everyone.
Thank you.
Bye.
Bye.